Okay, we're going to try to get an intuitive view of what divergence is by looking at this question. Now, divergence is going to be of a vector field. It's a function. We saw how to calculate it in the last video. It's simply just if your vector field here, they're two-dimensional. You have this vector field f, which is equal to some multivariable function p, and some multivariable function q in the j component. And so the divergence of a vector field, we saw how to calculate it. What it does is it simply just takes the x partial on p, and we get to add to it the y partial on q. And we had said that it measures the expansion or contraction of the vector field. You give me a point, and I'll be able to tell you whether the vector field is expanding or contracting or not changing at all by calculating the divergence. What it is the net change. If I put some small circular type of region around a point or even a square, what we want to look at is the net flow going in versus what's going out. If it happens to be that we lose magnitude, the magnitude going in is less than the magnitude going out, then what we have is a negative divergence. If we have the magnitude going in is smaller than the magnitude going out, then we have a positive divergence. And so for the point P1 represents a place where the divergence of the vector field is positive, greater than 0. While the point P2 represents a place where the divergence of the vector field is less than 0. What we say for P1 is that this represents a source. You're gaining power, you're expanding at the point P1, while at P2 you're contracting. The vector field is contracting there. That's called a sink. And so over here on these other vector fields, we can see that the divergence is going to be here we are contracting. This is going to be divergence less than 0. This guy is going to be divergence greater than 0. Here we go. This is going to be divergence less than 0. So we'll go ahead and say that this here represents divergence less than 0. That's a sink. And then down here we're going to have divergence greater than 0. That's a source. So the question then, what about 0 divergence? So you're neither a source nor a sink. Whatever you have coming in is what you have going out. The vector field isn't expanding nor contracting. And so what does that look like? Well, that's over here. We have, in both of these cases, the divergence of the vector field is equal to 0. Exactly what you have coming in is what you have going out. And so the magnitude of this arrow is the same as the magnitude of that arrow, and so on. The vectors are the same magnitude going in and going out. There's no expansion or contraction. And so this represents then a net 0 change. And then this is just an equal, that this vector field here would be something where there is no j change, and there's only a constant I change. This guy would be a divergence of 0, though, where we have these vector fields. The vector field, actually, here's an example of the vector field here. Let's say that this vector field would be something like 3, 0. No x or y change, and so no net change in x plus net change in y. This divergence would be 0. And so whatever comes in is going out, no expansion nor contraction. This is an example of what the vector field right here would be. So this gives us an idea of divergence. More than just how to calculate it, it gives us the intuition of behind what the divergence is at a particular point. The divergence of a vector field at a point.